This is a lecture on disk arrays or RAID systems for Comp 375 Computer Architecture and Organization at North Carolina A&T State University. There is an assignment on disk systems on Blackboard. Be sure to upload your solutions by midnight, April 8th. An individual disk drive can get up to about 1 or 2 terabytes, but some applications need lots of storage. Large databases sometimes have large mass storage needs, more than you can put on a single disk. So you have to store the information on multiple disks. And so you have to have an effective system for storing information across multiple hard drives. RAID systems are designed to provide storage across multiple disk drives and yet make it look like one large disk drive. RAID systems are a redundant array of independent disks. You have lots of disks, or usually 4 or 5, whatever, 6, however many you need, working together to store the information like one big file or one big database or one big file system. It operates as a single file system. And the benefit is sometimes they can increase performance and recover in the event that a disk drive should fail. In the mid-1980s, disk drives were big and expensive, about $50,000. In the picture here on the right, a woman is standing next to a 3380 IBM disk drive. That's one disk drive there. And she's not a midget. If I remember right, the box is taller than me. Now, about that time, home computers were coming out, and the PC disk drives were about 2/3 as fast as the big expensive drives, and they didn't hold nearly as much space, only about 20% as much space as the big disk drives. But they cost under $1,000 as opposed to the $50,000 or more of the big disk drives. So the people who were paying the big money began to wonder if they couldn't use a bunch of small drives put together. Originally, RAID stood for Redundant Array of Inexpensive Disks. After a while, they changed inexpensive to independent. RAID systems can be either hardware or software. You can buy a RAID disk controller that plugs multiple disk drives into it and makes it look to the operating system like one great big single disk drive. Here's a picture of a RAID system, and it holds 4 disk drives. Typically in these things, if one of the disk drives breaks, you can open it up, pull out the broken disk drive, push a new disk drive into it, and after a few minutes, it'll be off and running again. Off and running with multiple redundancy. During the meantime, it continues to keep on working. RAID can also be implemented by the operating system alone. Both Windows Server and Linux support the concept of RAID. All you have to do is build a computer with multiple disk drives and then tell the operating system that you want to use a RAID system, and it will use RAID technology across multiple drives. Users are unaware of the RAID features, so it's nothing that the user sees. You just see one great big disk drive out there. As you build systems with more parts, the probability of failure increases. The more parts a system has, the more things are likely to fail. If you look at an individual device's probability of failure is P, then if you have n of those and they all have to work together for the system to be reliable, then reliability of the system is P to the n. So for an example here, say you have 16 pieces together and each one has a 5% chance of failure, which is a 95% chance that it won't fail. So the probability that the whole system will continue to run at a given time is 0.95 raised to the power of 16, which is 44%. So 44% means a little bit more than half the time it's going to break, even though each of the individual parts had a 95% reliability rate. This The concept applies to computers, to disk drives, and to much larger systems. Consider sending a rocket into space. These rockets have zillions of pieces, and generally they all have to work for the thing to fly. And so each of the individual items has to be highly reliable. RAID systems come in multiple types. They've been building them and experimenting and coming up with new types throughout time. There are several that we're going to talk about today. You need to know both the numbers and what that number does. So RAID 0 is striping. We'll go over the details of each one of these. RAID 1 is mirroring. RAID 5 is block level distributed parity. And RAID 6 is dual redundancy. Nobody uses RAID 2, 3, or 4. They were nice experiments, but it turns out that RAID 5 is better. RAID 0 is to put files across multiple disk drives for high performance. It allows you to have large amounts of mass storage and quick access, but it doesn't do anything to improve reliability. In fact, the reliability is less because there are more parts and they all have to work for the system to work. The basic concept is that they will put the first block of the file on one drive, the second block on another drive, the third block on another drive, and the fourth block on that one. So every fourth block is on a different drive. So the first part of the file is on drive 0, the second is on drive 1, then drive 2, then drive 3, then back to drive 0, and so forth. So each physical disk has only 1/nth of the data. The advantage here is that you can read from all the disks simultaneously or write simultaneously. So after you seek and wait for the rotational delay, then the transfer time is 1/nth as long as it would be for a single disk. If you're reading and writing large files, the transfer time can be an important component of how long it takes to read. If you're reading and writing small files, then usually seek and rotation delay dominate. There's a website here that has pictures of the different RAID technologies. Here's how the operating system would see a RAID 0 system when it's managed by a hardware controller. There are multiple physical disks, but to the operating system and the user, it just looks like one great big disk. So all the data is on that disk, but in reality, it's spread across multiple physical disks. So when it reads and writes it, if you're reading and writing large quantities at once, you can write them across multiple disks at the same time, running a little faster. Another RAID technology is mirroring. RAID 1 makes two copies of the data, or actually makes a copy on two disks. You have one disk, which is just the way it would be if you didn't have a RAID system. Then you have a second disk that is an exact copy of the first disk. So everything that's written to the first disk is written to the same place on the second disk. So both disks are exactly the same, or a mirror image of the other disk. If one of the disks was to break, you can still keep on running with the other disk. This improves reliability. It has slightly slower writes because whenever you write things, you have to write it to both disks. Now, if both disks are on separate controllers, you might be able to write them simultaneously without much delay. Turns out you can do faster reads, not because an individual read is any faster, but if the system is busy reading information off the disk and then another application wants to read from someplace else in the disk, well, you can read from the second disk if the first disk is busy because they both contain exactly the same information. So the system can read from either disk that's not busy. The downside of this is that it takes twice as much physical mass storage to hold it. So if you have two physical disks, you only have one disk worth of usable storage. The second one is the backup, and you don't see that. The answer is C, 4. Okay, if 850 gigabytes of space is required, then it's going to take two physical drives to do that. So two 600 gigabyte drives will provide 1200 gigabytes of space. And then if you want to use RAID 1 in order to provide reliability, it'll take another two 600 gigabyte drives to back it up. So that's 2 primary, 2 secondary for a total of 4. Let's think about our digital logic for a minute. Consider the exclusive OR function. Say you have 3 values and you exclusive OR them together. And that gives you the answer X, which is the exclusive OR of each bit of true and false values. Now, let's say you lose one of those values A, B, and C. You can find out what it is by exclusive ORing, say X and A and C, and the result will be B. So what they do is they exclusive OR each bit. You read a block, and exclusive OR it with the other block bit by bit. Well, of course, they do it much faster than that, but for each, the first bit is exclusive OR with the first bit of the second block, which is exclusive OR with the first bit of the third block, and so forth, to give the first bit of the block X, and so forth. So they exclusive them all together. If you have drive A, drive B, and drive C, and then drive B breaks, well, you can recover it if you have the exclusive OR X just by exclusive ORing X, A, and C, and it gives you back the information that was on drive B. And so RAIDs 3, 4, 5, and 6 all use this concept of exclusive ORing to be able to recover information that was lost. RAID 4 has this concept. You have here 4 disk drives that hold the data and 1 disk drive that holds the parity block. Every time your system writes information, say it's going to write information across blocks 5, 6, 7, and 8, then it takes that information, writes that to the disk, and then writes the exclusive OR of those blocks into the parity disk. So if any one of those disks was to fail, you'll be able to recreate the information by exclusive ORing the remaining disks and the parity disks. So the system can quickly recover in the event of any disk drive was lost. The system can keep on running because all the data is there. Whenever it needs to get something that was on a damaged drive, it does the exclusive OR. It turns out, though, this system is not used very often. RAID 5 is the same concept, but they've moved the parity blocks across the multiple drives. It turns out with RAID 4, by putting all the parity blocks on one drive, that individual disk drive got heavily used and tended to become overloaded. So RAID 5 solved that problem by distributing the parity blocks across all the disk drives. It's the same idea. The data blocks are all exclusive ORed and then saved as a parity block. But a parity block is located on different physical disks in order to keep one disk getting overloaded. RAID 5 is a very common RAID system. RAID 4 really isn't used hardly anymore at all. It should be noted that it requires one more drive than that is required to hold the data. In other words, here we have 5 disks, and there are 4 data disks and 1 parity disk. So you can only have 4 times the disk size of actual user data. The other block is used for parity. Okay, if you have 4 physical disk drives, one of them has to be used as a parity disk, or at least the space of one, even if it's spread across all the disks, the space of one disk is used for parity. So you only have 3 of the 800 gigabyte drives you can use for data. And so 3 times 600 is 2400 gigabytes, or answer C. RAID 5 always uses the equivalent of 1 drive for parity. Only 3 of the 4 disks can hold data. If you're really paranoid about losing your information, you can use RAID 6. RAID 6 can survive the loss of 2 drives. If any 2 of the drives on the system fail, then you can still recover the data. It uses double parity blocks, and so it requires 2 additional drives So if you, in this case, we show 6 disk drives, but you only have as much data as would hold on 4 disk drives, because the space of the other 2 drives, although spread across multiple physical drives, is used for the parity blocks. So this can be used if you want to be able to recover from the loss of 2 of your drives. RAID 5 will survive the loss of 1 drive. RAID 6 will survive the loss of 2 drives. When you have multiple disk drives, it helps in performance if they all are spinning together. That is, after you do the seek and you're waiting for the rotational delay, you want the rotational delay to be the same for each disk. You want them to all come to the data at the same time. If you do a little statistics and think about this, typically if they're all synchronized, they're all spinning together, then the average rotational delay is 1/2 a spin. Sometimes you're lucky and the data is coming under the read head just as you want it. Other times you just missed it, you have to wait for it to spin all the way around. If they are not synchronized, then you can assume that they'll be split across the disk drive, each in 1/nth different location. And so you have to wait for the last one to get done. And so it's going to be n-1/n instead of 2, and that's considerably larger. Fortunately, almost all disks that are manufactured have the ability to be able to synchronize, so they can all spin together. Here's a summary of the different RAID systems that are in use. RAID 0 is just for additional speed. It uses n, if you want to hold n drives of information, then you need n drives. It doesn't require any additional drives. It can read and write the data faster than a single drive. On the other hand, if any of those drives fail, you're out of luck. It might be useful for temporary space, for a fast gaming system. RAID 1 is mirroring. It requires twice as many drives. Reads can be slightly faster because you can read from either drive. If one's busy, you can read from the other. Writes might be slightly slower because you have to write to both disk drives. If either one of the drives fails, though, you can keep on running with the other drive. RAID 5 requires 1 additional drive. So if it requires 4 drives to hold the data, a 5th drive can be used to hold the extra parity information. Reads are faster because it's striped across the system, so the striping like RAID 0 improves performance. Writes are slightly slower because you have to write that parity block. And if any one of the drives fails, the system will keep on running. RAID 6 is just like RAID 5 but with 2 parity drives, and so it can survive the loss of 2 drives. And almost all of these systems, or RAID 1, 5, and 6, if one of the drives fails, the system will keep on running and allow you to replace the broken drive while the system is running, which allows it to keep going. It should be noted that in RAID 5 or RAID 6, if the disk controller breaks, then you're left with disks, each one holds 1/nth of the information. None of the drives by themselves holds all the information. If you have mirroring or RAID 1, if one of your drives breaks, the other drive can be put in another computer and used perfectly well because it contains all the information. Okay, if you have 200 gigabytes of data, then you can divide that by the 80 gigabyte disk, and we'll take 3 disks to hold it. 3 times 80 is 240 gigabytes, and so that's big enough. 2 times 80 is only 160, it won't fit. So you need 3 drives to hold the data. Then you can use 1/4 drive for the parity space. So the answer D, 4 disk drives using RAID 5 will do this. Now, somebody may note that you could also do it with 6 drives with RAID 1. Yes, since it takes 3 drives to hold the data, you could have an additional 3 secondary drives. And that works. Although, who wants to buy 6 drives when you can do the job with 4 drives? Okay, here's the basic rules for RAID. First thing you have to do is figure out how many disk drives does it take to hold your data. So all you have to do is divide the size of your data by the size of each disk to find out how many disk drives. You have to round up to the next largest integer because you have disk drives in integral units. You can't have 2.5 disk drives. You have 2 or you have 3. So if the number comes out to a fraction, you have to round up to the next largest number. Now, that gives you n. If all your data will fit on one physical drive, use RAID 1 with 2 drives. So all the data is on both drives, just takes 2 drives, use RAID 1. If, though, the data will not fit on one drive, you need to put it across multiple hard drives, then use RAID 5, and you need one more drive than will hold the data. So if it takes 5 drives to hold the data, you'll need a 6th drive for the parity space. If you need to survive the failure of 2 physical drives, then use RAID 6 and add 2 additional drives past what it takes to hold the data. That RAID planning slide is all you really need to know to answer the test and the homework. Follow the process and you can calculate your RAID needs. There's a disk homework assignment on Blackboard. Make sure you answer the questions and upload your solutions to Blackboard before midnight, Wednesday, April 8th.